All right, so any questions about what we're doing today from the agenda or the reminders there at the bottom of the screen? All right. Yes. Yep. For the overall agenda in terms of what we're doing this week and next week, then just kind of making sure you're aware. So tomorrow we're going to be doing whiteboard presentations, and so when you come to class tomorrow, you don't have to have all your graphs completed, but you need to have enough of analysis done that you know whether it's quadratic, linear, inverse, so you can tell what the relationship is. I'm not going to ask you to reconstruct all your graphs for the whiteboard presentations, but I do want to have you go through all of the 5 required relationships and say whether you think they're linear, quadratic, or inverse. And if they're quadratic, which one is squared, right? So make sure you're working on that. Like I said, finish worksheet 3 for tomorrow. That's going to be the focus of our test review. And then with whatever time left, we'll start working on worksheet 4. As always, there's additional worksheets on Axis and Unit 3 with answer keys. You can also always go on to AP Classroom and watch the daily videos, go through the topic questions, all those things, great ways to review. So be preparing for that test coming up Thursday. I guess for you guys, it'll be Friday, B-Day. All right, so let's talk a little bit about some other uniform circular motion examples here. We talked last week about apparent weight, and that sometimes College Board will use that terminology, apparent weight, instead of using what's more precisely what they're talking about, which is the normal force. So this says we can sometimes call this feeling of heaviness or lightness, like when you're going over a hill in a car or over a hill or through a loop on a roller coaster. When you have that feeling of being heavier or lighter, we can call that apparent weight. But really it is the normal force. It's what we would draw in our free body diagram as the normal force. It's the same force, it's the same as the force of the surface pushing on an object. Now the picture is showing you another term that you'll often see. So we talked about apparent weight last week, but I also want to mention apparent weightlessness. So these astronauts in training are not actually on a space station or anything. They're actually just on a plane that's doing a nosedive. It's called the Vomit Comet. So it goes up to really high altitudes and just nosedives, so they're in free fall. The plane's basically in free fall and they're in free fall. So they feel weightless because there's no normal force. The plane is falling at the same rate they are. So there's nothing to push against. There's nothing to give them any support. So we call that apparent weightlessness. Obviously their weight didn't vanish. They still have weight. And obviously they are not in space because I just told you they're in a plane. So it's just the fact that the ground isn't lifting them at all. It's not bearing their weight. So they feel weightless. And you can see balloons and stuff floating around, and they're kind of floating around. So that is, whenever we talk about apparent weight, it's the normal force. If they use the term apparent weightlessness, what that means is the normal force or whatever is causing the tension or normal force, it goes to 0. So we're going to look at an example of that here in a minute. But they sometimes use that terminology. If they say find the apparent weight, they're really saying find the normal force. If they say find when it would be an apparent weightlessness, that just means find when the normal force is 0, or find when the tension force is 0, depending on what's causing the centripetal motion. All right, so let's look at a couple other examples of kinds of things. We've talked about roller coasters. We've talked about driving cars over hills and through valleys. And we know that centripetal force would be what's causing the circular motion in all of those scenarios. We know that if you're riding on a roller coaster, that the centripetal force of acting on you when you're in this position, if you're at the top of the loop, that seat is pushing down on you and gravity is also pulling you down. And so we've got 2 different forces. You can come grab stuff. We got 2 different forces that are both pulling towards the center of the circle. Now, another example would be if you've ever swung like a bucket of water in a vertical circle. You know that if you swing it fast enough, the water doesn't spill. And so in this case, they're talking about a bucket on a string or a bucket on a rope or something, and they're swinging in a vertical circle. And they're highlighting here that when the bucket gets down to the bottom of the circle, if you've ever done this or if you can imagine what it would feel like, Would it pull on your arm harder or less at the bottom? As you're swinging it around, would it pull harder or less? Harder. It would be harder than if you're just holding it, right? Because it's trying to go down and you're stopping it from going down and you're bearing its weight. Does that make sense? What about at the top? What does it feel? Lighter. And you could get a perfect speed, and some of you may have done this with, I don't know how many of you have swung a bucket of water, but even if you've done exercises with dumbbells or kettlebells or things like that where you're swinging them in arcs and circles and such, you can swing something up to the top and you get to that point where you can kind of just let go. And if you're just at the right speed, it won't fly off, because if you just have that correct speed, you kind of loosen your grip and it's not going anywhere until you have to grip it again to bring it back down, right? There's that speed where you're kind of making the tension force in your arm zero. There's a speed with this bucket where if I'm swinging the bucket around, I could make it so that it keeps moving, but I wouldn't feel any pull on my arm because I've just got the perfect speed where that tension force just goes to zero. If we're thinking about that roller coaster, there's a certain speed where when it goes up through the loop, the passengers would feel weightless. They would feel like the seat's not pushing on them at all. Now, chances are they would not design a roller coaster that does that, because if it did, they would have to have very good harnesses and belts and stuff to keep people in, because if they're squirming around or something and there's no normal force, that would be a much higher risk. So, but you will feel less push of the seat at the top of that loop. All right. So if we think about this bucket on a rope here, swinging in a vertical circle, it's just like the other scenarios we looked at with the car going through the dip last week. The tension force has to be larger than the weight, and so we could find the net force by taking tension minus weight. But because this is moving in a circle, the net force is centripetal, and centripetal force has the equation mv squared over r. So we can find the net force two ways: tension minus weight, or mass times velocity squared over r. At the top of the swing, there's that, like we said, that magical sort of speed where this tension force vanishes, but if it doesn't, if there's still some tension force, it is downward in direction. And the weight is also downward in direction. So we wouldn't subtract them this time because they're actually pointing in the same direction. We add them, but it's still centripetal because it's still moving in a circle. So we've got tension plus the weight in this scenario. They're both pointing the same direction. In the previous case, they're pointing opposite directions, so we have to find the difference between them. Here they're pointing same direction, so we add them up. Both cases it's circular, so both cases are equal to mv squared over r. Yeah, Chris.
For the roller coaster example, this, you can't consider it like centripetal force if you like fall out of your seat and you're only being held there by your harness, right?
Well, it depends on if you keep going in a circle, but chances are in that case you've broken the centripetal force. If you're going slow enough, you've actually fallen. Now you're in free fall till something redirects you. So yeah, at the point where the seat belts and the straps start redirecting you, then they would move you back into a circle, but there would be an instant there where you wouldn't truly be following the path correctly if it went too slow. So this question, like I was mentioning before, there is that velocity, and they usually phrase it this way, like, what's the minimum velocity for a bucket to make it around the circle without the water spilling or something like that? So that would be, so if I go too slow and now the bucket starts falling, now the water's gonna fall out, right? So, but there is a speed where it won't start falling. It'll follow the path, but when I get right to the top, my arm will be totally relaxed. I won't be pulling at all. There's a certain speed. If I go slower than that, it's a mess. We spill all over the place. If I go faster, I just feel more tension in my arm, but it's fine, right? So I can go faster than that speed and keep it working. I can go slower down to a certain spot where my tension in the arm will just be totally relaxed. If I go slower than that, I make a mess. All right, they're wanting to know what is that minimum speed where it doesn't make a mess, but the tension in my arm would be relaxed. I wouldn't have any tension pulling. And so here's what the free body diagram would look like. The tension force that we saw in the previous one, this tension force is just gone. We're saying that reached zero, but it was enough to still keep it in the arc. So now it's just the weight of the bucket in the water that's creating that centripetal force. So the equation, instead of being tension plus weight equals centripetal, now it's just weight equals centripetal. And if we want to find what that velocity is, what happens to the masses here? They cancel, and then we multiply both sides by r, and then we square root both sides, and we could find that velocity just by taking the square root of g times the radius. We don't need the mass of the bucket. We don't need anything. We don't need any of the details really, except for the radius. And just if we're on Earth, we know g is going to be 9.8. That would be the same for the roller coaster. If you wanted to find the speed that the roller coaster would go through the loop, and the passengers would just at like the minimum speed where it would make it but stay in contact, that would be the same idea. Instead of normal plus weight, it would just be weight. And so it's going to simplify down to this same equation. So I put this one in a red box on the screen here, this equation, because you could figure this out when you're solving a problem. But if you sort of have this tucked in the back of your mind as an equation that might help you solve a problem quicker because you remember it, this is one of those equations. This minimum velocity question is quite common. I can't guarantee it's going to be on your test. I can't guarantee it's going to be on the exam in May, but it's a very common question. So this is one of those where if you've been keeping a list of equations where, you know, these are ones that might be helpful, but that you don't necessarily, they're not on the equation sheet from College Board, this is one of those. You'll need to make a note so you don't forget what it's meaning, but so this would be a vertical circle, trying to find the minimum velocity in a vertical circle. But it could be a bucket on a rope, it could be a roller coaster, it could be a car going over a hill, any of those circular motions. That would be that minimum velocity where it's just the weight that's keeping it in a circle, and the normal force or the tension force or whatever else canceled away. Definitely not one College Board will give you. They're just kind of expecting that you'll put this together and simplify it down. But if you happen to remember it, it will make your process quicker. And that's it for today. Just a few examples, just one kind of common question I wanted to mention that you should be at least have seen before, and we'll practice them like that tomorrow as we finish our review. Mm-hmm.
So the centripetal force, like the force circle, then?
Centripetal force is always to the center of the circle. Yeah, centripetal literally means center seeking.
Right. Okay.
Yeah. So it is the force that's, objects always want to go straight according to Newton's first law. They either want to stay at rest or go straight. So to make it curve, there has to be a force pulling it so that it doesn't just keep going straight.
Oh, okay. So it would be like the sum of the tension and gravity, but you wouldn't like add it as a separate arrow.
Well, that's what this is. So this is tension and gravity. But this question is a very specific question here where they're saying, what's the minimum velocity that would keep it going in a circle, but where there's no tension? So where if you were doing this yourself, your arm could be totally relaxed at the top.
Okay.
So in this scenario, they're saying your arm's not totally relaxed. You're pulling down with this much force.
And that makes up part of the centripetal.
Yeah, so that's why we have to add them together here.
Okay.
But then if we slow it down a little bit, there's going to be a speed where that tension force cancels out, and then it just becomes this. And then if we slow it down anymore, it just spills everywhere because it won't stay in the circle anymore.
Okay.
Again, this only works for vertical circles. This doesn't really apply for horizontal circles, but for vertical circles, this equation can be pretty helpful. Any other questions?
Yeah, I
Alright.
have a question.
Yeah, go ahead.
So, like, if a question was asking you if it was still uniform circular motion, like at the top, and it gives you like a force diagram, and there is like tension or normal force, would it be like automatically uniform circular motion because it has
So, a couple things to say on that question. One, they'll almost never give you a free body diagram. You'll have to draw that yourself to figure it out. And then secondly, the context of the question is what's going to tell you it's moving in a circle more than any diagram they give you. So if I understood your question, It's not gonna be from a picture or anything, it's gonna be basically the context of if the object is a roller coaster going over a hill or through a valley or a bucket on a string swinging in a circle. It'll be clear from the context that it's circular motion, but they won't generally give you any kind of free body diagram.
Okay.
They will often ask you to draw one yourself though.
Okay, thank you.
So that's why we're seeing all these free body diagrams, because you need to be able to draw these. So if they give you this scenario, they may say, draw the free body diagram when the bucket's at the bottom of the swing, so it's this. They may say, draw it when it's at the top of the swing, so it's this. And then they may say, well, draw it when it's going at the minimum velocity where it would actually still keep going in a circle, but the tension is no longer there, then it's this. But they're never going to draw those for you. If anything, they're either going to ask you to draw them, or they'll just expect that you do in part of your problem solving process. Okay, so these notes are to help you visualize what you would need to do, not what they're going to give you. All right, any other questions? All right, so not much different today. I mean, it's all the same relationships with cars going up and over hills and down through valleys, or roller coasters. We did those last week. It's all the same relationships as what we did last week, but the new kind of twist is, well, what if they asked you about this minimum velocity idea? Nothing about the free body diagrams today are any different than what we did last week. Same idea. But now they're just asking another twist. And if it is a vertical circle and they ask this question, now you could always solve it yourself. You could just figure out the free body diagram, put these two together, recognize M cancels, solve for B. It's not like that's incredibly difficult. But if you recognize, oh yeah, anytime it's a vertical circle and they want minimum velocity, there's that equation. I don't have to rederive it. I can just use it, okay? So you can always derive it, but if you know it, just will speed up the process a bit. All right, so let's continue and review for the exam by looking at worksheet 3 here. We're going to look at just the first page. Hopefully you had a chance to get at least that much done. So let's look through this first problem here. It says we've got a woman flying aerobatics, and she's executing a maneuver as illustrated below. So she is flying this plane in a circle, a vertical circle. Construct a quantitative force diagram, and again, this Arizona State curriculum always says force diagram, and what College Board always asks for is free body diagram. So force diagrams are a little more general. They don't have to always have a single dot. You can draw them a little more randomly. Free body diagrams always have a single dot. All the arrows point from the dot. They all radiate away from the dot. They all have arrowheads. Everything's connected. Just those College Board rules that we reviewed a couple months ago. All right, so in this situation, because she is upside down, the seat is above her, right? So the normal force of the seat's pushing down. And her weight from the gravitational force field of the Earth is pulling down. So both of the forces acting on her are downward. And so would we add these or subtract these to find the net force? Add them, they're both going the same direction. And if we add them to find the net force, is this net force centripetal?
Yes.
Yeah, she's going in a circle, so the net force must be centripetal. Yeah, Chris?
This probably isn't very efficient, but if you wanted to figure out if this is the minimum speed or not, could we plug what we have into the equation that you gave us?
Yes, yeah, you could.
Alright.
Yeah, Kenny?
Why isn't there a normal force like seatbelt keeping her in the seat while she's upside down?
She doesn't wear a seatbelt
Why doesn't she fall out?
because they're going fast enough.
Centripetal force.
Yeah. If she was going too slow, she would fall out.
Okay.
Yeah, so if they added something about a seatbelt, I've never seen them do that, but that would be a force upward. But since they're not saying anything about it, we're assuming there isn't one, which probably isn't realistic, but if they don't say anything about it, don't assume something's there. Yeah. All right, so it is centripetal force. So in the box over here on the right, I have kind of a list. Okay, well, the net force would be centripetal because it's going in a circle. And it would be the normal plus the weight force because they're both pointing the same direction. So there's two kind of ways to think through how we can find the net force, either thinking about it as centripetal or thinking about it as the sum of those two downward forces causing the centripetal motion. And then the rest is just them doing the math. So first they figure out what is Fg, and that should be second nature by now. Take her mass times g. They're using 10 here instead of 9.8. And you notice they're using, instead of the acceleration version of 9.8 meters per second squared, they're using it as newtons per kilogram, which is just equivalent units. So they're thinking about this as more of a force field compared to an acceleration. Doesn't matter. It's like calling me a teacher or a coach or a grandfather, like that's all just me, right? It's the same person, I'm just different role. 9.8 is going to be acceleration due to gravity, it's the force field of the earth, whatever you want to call it. You can change the units, you can describe it differently, but it's still the same thing. And they're just using the version of 10 instead of 9.8. So the woman's weight is 550 newtons using 10 instead of 9.8. And then because it's centripetal in nature, this net force can be found as mv squared over r, because v squared over r is how we calculate centripetal acceleration. So if we look here at their substitution, they just put in the mass, 55 kilograms, and then that whole messy looking process, 235 kilometers per hour times 1,000 meters per kilometer times 1 hour over 3,600 seconds. That's all just what you need to do to change it from kilometers per hour to meters per second. You have to make it meters per second because newtons is a kilogram meter per second squared. So your units have to match. You can't just leave it in kilometers per hour. All right. So if they give you something in kilometers per hour, you have to convert it to meters per second so that your units work. And then, so they put the mass in, they put the radius in, they do that little computation to figure out what the speed is in meters per second instead of kilometers per hour. They square it because it's v squared, and they get 617. Now in the next row, they're just showing, okay, back to the previous thought, net force is not only mv squared over r, it's also the sum of these two. Now I know the net force is approximately 620. We got 617, but they're just rounding because of sig figs. Since the 55 only has 2 sig figs and the 380 only has 2 sig figs, they're just rounding 617 to make it 620. So I know the net force is 620 because that's what I found for my centripetal force equation. I know her weight is 550 because that's what I found up above. And so I can subtract to find the normal force. So in this flight, the seat is actually pushing her down at 70 newtons. So does she need a seatbelt?
No.
She'll stay in her seat, okay. She'll feel pretty light. 70 newtons isn't very much. She'll feel pretty light in the seat, but she wouldn't fall out.
Could that be like an AP test question? Like, is this velocity enough for them to like need a seatbelt or something?
It probably could be. I haven't ever seen one like that. More often it's find the speed that's the minimum. That's like the most common that I see almost every year somewhere. Sometimes multiple choice, sometimes FRQ, but finding that minimum velocity is a super common question. I wouldn't put it past them to ask that because you could do it. I just haven't seen it yet. But they change every year, so you never know what's going to come up. All right, so what is the centripetal force in this scenario? How much? 620. Okay, 620 newtons is a centripetal force. It's both her weight and the normal force. Her weight is pulling her towards the center of the circle, and the seat is pushing her towards the center of the circle. So we have to add them together. Questions? Now, this is a really common question. Sometimes they give you numbers like this. Sometimes they just want you to do it all with variables. All right, so you have to be comfortable thinking through it either way. So make sure you understand, not just don't just memorize a sequence of steps, because it'll never be exactly the same question. It'll always be a little bit of change, or they don't give you numbers. You got to actually do it with just variables. So try to make sure you're understanding why you're doing what you're doing here, not just memorizing steps. All right, the second question. 6 children run on a track with equal speeds. Their masses are expressed as multiples of mass m, and their path radii are expressed as multiples of r. Rank the centripetal acceleration of the lettered children from largest to smallest. And so they have here under the explanation, centripetal acceleration is v squared over r. So does the mass even matter? No, it's just v squared over r. What did it say was true about their velocity?
Equal.
Yeah, they're all going at equal speed, so the velocity isn't changing. And if the r is in the denominator, the bigger the radius, what's true about the acceleration?
Small.
Smaller. This is our relationship here, right? Acceleration is v squared over r. So the bigger this gets, the smaller that gets, right? The smaller this gets, the bigger that gets. Okay. So student A, Andy, and student D, Danny, they have the smallest radius, so they have the largest acceleration since they're all going the same speed. And then Betty and Ernie, they're in the second row there. They're the next smallest acceleration because they have a little bit larger, next largest acceleration because they have a little bit larger radius. So that decreases their acceleration a little bit more than Andy and Danny. Remember I said they were, you can never remember their names. Then we get to the third row, they have the biggest radius, so they got the smallest acceleration. So Cindy and Frank, they're the least amount of acceleration. Questions about how we process that relationship and rank them? Ranking questions are also super common in multiple choice.
Well, this is kind of not like on the question, but
Okay.
so with the centripetal acceleration, then here'd be like the both like the sum of like the friction and then like the applied force.
For this,
Yeah.
well, here
Wait,
the
not that I
centripetal
can
acceleration would be hard to, anything that's like a person running,
Yeah.
it's going to be mostly friction. The applied force maybe to some degree, so you would never be asked to calculate it in a scenario like this. That's why it's a ranking question.
Okay.
Yeah. All right, part B says rank the centripetal force. So if it's a force, does the mass matter? Yes, because F equals ma, right? So now if we think about the force equation, we're trying to figure out ranking the force. So what's true about the V? Yeah, they said that they're all running the same speed, so that's not changing. So we can ignore that, right? So really we're just thinking about, well, what is the mass to radius ratio? The largest mass to radius ratio gives us the largest force. The smallest mass to radius ratio gives us the lowest force. So if we look at Andy, 4 mass, 4 radius, what's the ratio of mass to radius? 1. How about Danny? 1/2. So Danny is half of what Andy is. So we've got those two ranked. Right? How about Betty or Benny or Billy, who I forget who B was? He's 1/5. So that's the smallest so far, right? How about Ernie? 3/5, so 0.6. So that's between 1 and 0.5, right? How about Cindy? 1. That's the same as Andy. So they're the top. They're tied. And then how about Frank? 1/3. So that's down there, not all the way down. 1/5 is the smallest, but 1/3 would be, right above that. So we don't have to worry about velocity. We're just, what is the mass to radius ratio? And then we can rank them. All right. So Andy and Cindy are tied, and then it's Ernie, and then Danny, and then Frank, and then Betty. All right. So again, ranking questions, very common in the multiple choice portion of the College Board exam. And there's another one on this worksheet. If you haven't finished the worksheet yet, you'll get to it later and have to think through some things like this. But particularly in scenarios like people running where there's a lot of body movement and stuff like that, it's hard to calculate it directly. So they'll give you more of this kind of a question. Things that are smoother, like a bucket and a roller coaster and cars, that's generally where they have you actually calculate values. All right, any questions on page 1? We need to stop there so I can give you some time to get with your partners. All right, so with your lab partners, you need to think about your TOA-GAMR conclusions. If the question is, if your TOA-GAMR is force and acceleration, well, think about the relationship. What is force and acceleration, right? F equals ma. So force and acceleration should be what kind of proportional? If it's F equals ma? Directly, should give me a straight line, right? What if it's tension, force, and velocity? What should we expect? If it's force and velocity? V is squared, so quadratic, right? If you're thinking about, well, how do I graph these? Well, if I were graphing these and I had force, since this is the equation we're learning right now, I would put force on what axis? If this is my equation. Y equals mx, right? I would try to graph it in a way that's going to match the patterns that I can, or that I have here in these equations we've been learning as much as I can. And then you can see if your data actually matches. So if you're graphing acceleration and velocity, that on the y, that on the x, and you should see what kind of relationship, hopefully. Quadratic. What if it's a versus r? Should be inverse, right? Hopefully. Now your data may not be great, but if you think about the equations, it should help you decide, well, how should I graph these things? And what shape should the graphs look like? So then you can try to do the fits that hopefully match what you should expect and see if your data gives you something reasonable. You won't be getting r squareds of 0.999. So just hopefully it's reasonable. So get with your group, talk about your relationships with the TOA-GAMR questions, consider all that, and use your time well. And then Dominic, when you get back, I don't know if you heard me talking to Charlie earlier, but he just got back today. So if you're able to come back tomorrow, I could get you guys working on getting your own data, or I can help you both get set up with a simulation where you can generate data through a simulation. You can let me know how you want to do that.
Okay. Do you want us to come in at like lunch or something?
Yeah, that'd be perfect if you're able to do that.
Okay. All right. Sounds good. What do you want me to do now, though?
Say that again. Can you repeat that last part, Dominic?
What do you want me to do right now?
For right now, just make sure you're preparing for the upcoming test, I guess.
Okay. All right. Thank you.
You're welcome.
Outside corner of the zone gets it out.
I had like 16 seconds.
Yeah.
So I put David in the low.
Yeah.
Well, Hail Mary.
Yeah.
So I clear them all. We missed the tap.
Where's the slide?
And then the next time I set it all up, it's like I forget to set up the handle. And I slid. So then I was like, shoot, should I just let it go?
Yeah.
Wait. I guess the weight just affects this, which is then part of the whole.
So then I'm guessing
So it
that
kind of
you-
makes sense that.
that was not linear to me. This
Wait, go back here.
I think you just did linear fits and hoped it was right. Did you actually do different regressions and check your R squared values? Okay, yeah. Need to do that so that you can get some idea. Now, some of them may not have a relationship, so if you get a real irregular or like horizontal line, then it's just no relationship. But to me, this looks like it could be curving this way. To me, this looks like it could be curving this way, but it's hard to tell. Yeah, without seeing on the, did you do it on a calculator or just scan through everything?
I did this on desk mode.
Okay.
The line was hand drawn.
And so tension, force, and velocity, since you put velocity on the other, that would be like velocity equals, so if you put that on the y, or on the y, then you would, yeah, it does look like a square root. And then that's what acceleration and force. So that one should be pretty linear if it's force and acceleration.
Okay, so I can leave this one linear, this one
We have it all, it does one.
and this was the radius versus velocity. So velocity would be y. Be like
Making sure it's supposed to do.
Yeah, so if you, it's which one's radius and velocity? So if you put radius on the other side, r equals
that
v
one
squared
side
over a.
y is the y.
Yeah, so it'd just be like v squared equals
We have the tables.
ra.
I saw two, do we
Try
all
to
three
save it
done?
again. Well, the other one was like.
Okay, see what I'm saying?
So that'd be
Right.
here.
I don't know the
No,
calculation.
because the velocity is squared. Yeah, it should be.
I'm not entirely sure how like the
Try to
weight
say
of
you can
the
use save
log
coffee.
fully works into these because like it affects the time, which then affects the velocity, so it kind of makes sense that this should be a square root, but
Does it seem to be,
Go to OneDrive and upload it to.
Is that, that's acceleration and weight?
acceleration.
That's pretty zoomed in though. Like if you put it down to 0, because if it really has a relationship, we would want to see it. Yeah, that was, you just did data, so that's what it is, but you can do Windows settings, yeah. Just make your Y 0.
I just did them over here.
Does this have the other data on it?
So-
Yeah, the other data is over
It's
here.
possible that's got some curve to it, but it's also possible that that's supposed to be a straight line.
So there's no relationship.
Yeah, go back to the other previous one.
Only graphs for 5, and there's one option.
Same thing here, if you go
It's a
to make
line.
it 0.
So wait, all can just do start with like.
I guess it's still.
Yeah, it's
Do
a little,
one,
little
like,
bit of
add
an
it to
angle
the
there.
log.
So you could say, you could think it may be linear, you might think it's just a horizontal line, so.
I guess there's
No
only three
relationship
times
to
we
the
all just
velocity
take
of the
one.
equation.
Yeah, so
You know what I mean?
is the velocity what's causing the equation to change? Or sorry, causing the velocity to change is the, sorry, is the mass what's causing the velocity to change is what you're trying to figure out.
This one's the one where.
So I'm not gonna answer it, I'm waiting till we have the.
I'll get back to you.
Exactly was that Excel, like the software.
So he says that both.
Yeah, it's on unit three.
horizontal
Yeah.
line.
Yeah.
Topic 2-3. It's right under the rubric, it's like stop or ladder.
Oh, we changed
Class
the
data or something.
acceleration for the attention force, yeah.
If you look at the equations, it's
They're
not,
changing.
The weight on the, what are the other, what's the other stuff?
Why are those numbers so weird?
And Newton.
figure it out and then we'll compare it to this definition.
There be one purpose for the whole one, or one purpose for
Yeah, we wouldn't have done this.
You could just write one purpose, and I've had students do it a couple ways, I've had some to say, to obtain a graphical math equation, and then list the 5 things that we evaluated, like velocity, acceleration,
Radius.
and
That does not make sense.
stop or dash. Or just like list the 6 things that you compare, like this versus this, versus this, so you don't have to say it, you don't do the whole thing 6 times, just do like.
Where's the rubric? I need a rubric.
Yeah, it is.
You probably get a graph, right?
Cause we know that cell that only comes straight up outliers.
Okay, I'll just do the first one. I'll make those 2 graphs.
Yeah.
Can I just ask these 2 questions?
Yeah.
So,
First question is, that's not what our data was, right? Our data showed that as the radius got smaller.
Like, you get it.
it's the way this graph frequency.
Well,
Yeah,
radius
it
and
literally
velocity
means
are
per
directly
second.
proportional to the distance.
Sure.
So,
Like neither of those is for
Sure.
I'll
velocity.
get this stuff.
second, oh yeah, you're negative 1 power.
So yeah, this is, that makes sense, let's
Okay.
Or
go around.
From my outside.
per second, so 4 cycles per second, 4 revolutions per second, 4 trips per second, like.
Okay.
There was none.
Oh, and that's why the frequency.
If I have to write it,
It's
like,
like, and you don't use that
Velocity goes-
for period, then it's like.
No, because they're reciprocal, so, because period is seconds, so,
Do you have one of these?
yeah,
Yeah.
period would be how many seconds per revolution.
Because there's no
And frequency is how many
correlation,
revolutions per
because
second.
as radius changes,
They're
both
directly
things change
reciprocal.
by different
Like
amounts.
Davis 4 in the middle and then.
So, if your
Oh, yeah,
frequency
there's
is
one
4, that
place
means you're
on the
taking 4
It's like a
cycles every
screen at
second,
the tight end.
which means your
Like,
period is a
I
fourth
tried it
of a
once, it
second.
didn't work yet, but I'll figure it out. It's like a play action with the running back and then it's like one to the other side.
Yeah, if your
It's like what the
frequency
Chiefs
is
do now.
4 hertz, that means 4 cycles per second.
Oh, yeah.
So your period would be 1
They have a
fourth
ton
per
of
second, so that
They
means
have a
1
ton of
Oh, I should look up like the most,
They have
yeah.
a ton of like read options.
and then the
So
other
just call
question I
like
had
read
was-
options.
I don't think my TV's fast
Like,
enough.
circle line and stuff, so like,
Yeah, our field is
like,
nice.
okay.
The bubble screen
I
I
guess
use a lot. Russell
You
Gage.
are at like the
Get
bottom.
some nice yards there.
Our field is nice. They're inside zone for plays, but then like
Then
there's two receivers that
grab
rush
it
down,
down,
one guy's
or
coming back.
forward,
So like if there's a
up,
man,
and
that's
that
choice.
force is up.
What else is so soft? Doesn't catch it.
Then,
Pass. There you go.
He's gonna be getting out of there soon.
so then
Nice.
your, force that would be.
How comes the contract?
And minus that.
Yeah.
Like I fully guarantee.
Yeah,
that, so
if something's moving in a circle, the centrifugal force is the net
I
force.
would guarantee it's all the money you can
And
cut.
in this case, the net force is that much.
Inside. Yeah, then so if you like.
Cut him, that's a penalty.
Same thing.
Is that how it is in NFL? I feel like it's
So you
slightly.
know your net force.
Yeah, it's.
No.
They're way more calm.
Is the resign a player?
I didn't get that.
Yeah, centrifugal force is the net force. If there was no net force, it would just go in a straight line.
I have like 81 cap space now.
There has to be a net force.
Oh,
Like
seriously?
acceleration.
So I already signed Calvin Ridley.
It's just
But
acceleration.
I think Tyreek Hill's gonna be
Any
free,
direction,
so
yeah.
that might be
Okay.
why. Isn't he?
Yeah, he should be. The Chiefs probably get another.
A little bit, yeah.
I think they're gonna let him go.
This compromise data,
Yeah.
you can only
That's
really
my
use
one
the
change.
data from one group, right?
Yeah,
All
yeah,
these
that's it.
variable
Yeah,
different.
exactly.
Alright,
Yeah,
Okay.
so we only have 5, that's fine though, right?
5 points.
5 points, yeah.
Yeah, it's, unfortunately, it's not ideal because you don't have a lot of data points to consider, but it's the best we can do. But I think we ended up with like 7 groups, so across the classes, we'll be able to draw some good conclusions.
Yeah.
hopefully.
At least you got Tyreek 2.0. I'm getting Tyreek.
All right, we are out of time. Hopefully you had enough chance to at least make a plan for tomorrow with your group. Bring back worksheet 3 completed.
Can I like switch users and just go to Chiefs?
I'll get back
You're
to you.
welcome.
Wait, like, it'll tell me in a second or you don't know?
I'll tell you.
Yeah, like,
Add that.
oh, sure.
He's like really, he kind of lost his spot though, Jared McKinnon.
Yeah.
He fell off so hard.
Imagine if I had jumped instead of Clyde.
I forgot they took him.
Clyde was in the first, or on the second.
Went before Taylor.
Yeah.
I think. Yeah, Taylor was Wasn't there an Ohio State back then?
This year, try to start
You
with.
can, it's back there if you want it. We're gonna go over it in class. If you want it ahead of time, you can grab it.
Thank you, Mr. Wood.
You're welcome. You too.